Good day and welcome back. This will be our first of the video series dealing with things called quadric surfaces. And the goal is to introduce what we'll think of as a quadric surface, which is a three-dimensional version of a conic section. And we'll see a technique that we can use to sketch not only these surfaces, but really apply to many different surfaces that we'll encounter throughout the semester. And we'll also kind of just build up our recognition of these common surfaces so that as we encounter them later in the course, they'll become almost second nature to us. But the starting point of our discussion is to really remind ourselves of three important conic sections that we probably encountered in a previous pre-calculus course. These will be very useful, as we'll see in our future examples. So to begin, a parabola is something that we're probably all very familiar with. The generic equation of a parabola is something like y equals ax squared. And if we want to be able to visualize the graph, I'm going to say there's really kind of two cases to consider. There's the case where a is bigger than 0 and a is less than 0. When a is a positive quantity, this parabola opens upward. And graphically, we have this kind of standard graph. Think maybe something that looks like x squared. It hits the origin. And depending upon the value of a, the smaller it is, kind of the wider the parabola would look. The bigger a is, kind of the steeper or skinnier the parabola would look. When the quantity a is negative, the parabola would open downward. So the standard example would be to think of something like y equals minus x squared. The next conic section that we should be familiar with would be an ellipse. So the equation of an ellipse is typically written in this form: x squared over a squared plus y squared over b squared equals 1. And graphically, we think of an ellipse as something that looks somewhat oval in nature. So I'm going to just draw a generic picture of an ellipse, and then we'll label some intercepts. So roughly speaking, something of this form. Now, note, if we wanted to find the x-intercepts occur where that graph crosses the x-axis. So they would be of the form something, comma, 0. So if y is equal to 0, and you solved for solved for x would be plus or minus a. So those x-intercepts occur at minus a0 and a0. And similarly, if you wanted to solve for the y-intercepts occur when x is 0. And if you set x equal to 0 and you solve for y, that occurs at plus or minus b. So simply looking at this form, we immediately know that we have an ellipse, and then based upon a and b, we have the x-intercepts and the y-intercepts respectively. And note that the maybe most common example that we see of an ellipse is a circle. So a circle is an ellipse with a equal to b. The next conic section, and the one that I think we probably struggle with the most just in terms of recognizing and sketching, would most definitely be the hyperbola. So a hyperbola has an equation that looks very similar to that of an ellipse. It's just that plus sign separating the two terms on the left becomes a negative sign. So the generic form of a hyperbola is x squared over a squared minus y squared over b squared equals 1. And graphically, what a hyperbola will look like is two parabolas opening away from each other. And the question is really just kind of, do they open away from each other along the x-axis or along the y-axis? And how I remind myself of this is to think of the intercepts. If you wanted to find y-intercepts, you would set x equal to 0. And just for a moment, imagine this first term was not there. Then you would have a negative quantity on the left equals a positive quantity on the right. So there are no y-intercepts. But if you were to set this y term equal to 0, you could solve for x. X would be plus or minus a. So there are x-intercepts, just no y-intercepts. So that tells us that this is going to be these two kind of parabolic shapes opening up away from each other along the x-axis. And this would be a0 minus a0. And this is just a very generic big picture overview of these common conic sections. There's all kinds of details that one could include if you want it, but what I'm going to suggest is just kind of this big picture understanding. What does the equation give us, i.e. a parabola, an ellipse, or hyperbola? And once you've identified the conic section, we should be able to sketch one of these curves. And in the next video, we will very clearly see kind of where this all comes from. All right, so one more example before moving on. Let's go ahead and sketch the surface given by x squared plus y squared equals 1. And note, as we've seen many times, the key word here is a surface. And in class, I would typically ask you all, what word or how would you describe what this surface should look like? And we want to make sure we use the correct C word. It's very tempting to say circle, and it will be circular, but it turns out it's not a circle because it's a surface. So let's hold that thought for a moment and see what the graph looks like. So we want to sketch this in 3 dimensions. So we have our coordinate axes, x, y, and z. And the observation I want to make to help sketch this surface is one that we made previously in our maybe first video of the semester. And that is to think about what is not present. So z is not present in this equation x squared plus y squared equals 1. So what we want to do is maybe think, what does this surface look like for the simplest possible value? Well, if z is equal to 0, i.e. we're sitting kind of flat in this xy plane, then our surface would intersect that plane in the curve x squared plus y squared equals 1. So this would be a circle in the z equals 0 plane. And I can very easily sketch a circle in the z equals 0 plane. So it's a circle of radius 1 centered at the origin, but specifically just the portion in this z equals 0 plane. So it hits over here on the y-axis at 1, the x-axis at 1. So now you say, okay, well, how about a different value of z? Pick your favorite value. Let's call it k. For z equals k, z is not present, so you still get x squared plus y squared equals 1, which is now a circle in the z equals k plane. So if k happened to be, let's say, a positive quantity, in that z equals k plane, what we have is the circle x squared plus y squared equals 1. So it's the exact copy of the circle we have in the z equals 0 plane. It's now shifted just k units upward. And now we probably see the correct C word to use to describe this. It's going to be a cylinder. No matter which plane we are in of the form z equals something, it's always going to be that same exact circle. So the word that I would use to describe this is a cylinder, and more specifically, it's a cylinder wrapping around that z-axis because the z variable is not present. And what we've actually introduced here is a method that we are going to use for sketching surfaces that we will refer to as the method of traces. So these equations are what we call traces. More specifically, they are the intersection of the surface with a plane of the form x equals k, y equals k, or more specifically in this case, z equals k. And if you know what these traces are for a given surface, they give you kind of a frame of what it looks like and should hopefully allow you to sketch the surface. So now that we've seen an example of maybe a standard cylinder, something that we could easily visualize being called a cylinder, I do want to note that as the semester goes along, we think of cylinders a bit more generally in Calculus 3. So moving on to the top of that second page of the note packet, the surface x squared plus y squared equals 1 is a cylinder, but I'm going to note that also z equals x squared is a cylinder, which might sound awfully surprising. But in general, a cylinder is a surface that consists of lines that are parallel to a given line and pass through a given plane curve. And we don't need to worry too much about this definition. Let me just kind of note that in general, we will recognize a cylinder when a variable is not present. So typically, when a variable is not present. Where with the cylinder from the previous example, it's the z that's not present, but with z equals x squared, it's the y that is not present. And just to make sure this definition makes sense, it's a bunch of parallel lines that pass through a given plane curve. So with the example we had of x squared plus y squared equals 1, we have this curve, x squared plus y squared equals 1, which is our plane curve. It sits in the xy plane. And then we want all lines that go through that curve and are parallel to the z-axis. So if you look at all lines going through this parallel to the z-axis, you get that cylinder that wraps around the z-axis. And similarly, and I know it might seem like a strange example, if you consider z equals x squared. If you look in the y equals 0 plane, so in this zx plane kind of coming out of the screen at us, z equals x squared is just a standard parabola opening up around that z-axis. So roughly speaking, this is kind of hard to sketch, but it's just a parabola and it's coming out of the screen towards us. And in these y equals traces, I find them to be the most difficult to sketch. But every y equals k trace is exactly the same parabola. So one way to think about it is you just take this parabola and you just drag it along the entire y-axis. So if you wanted to know what it would look like, this is just drug along that axis kind of indefinitely. And if you go to any value along it, you have kind of this parabolic shape. And how I typically would explain something like this is it looks like a big, huge parabolic horse trough, except for the fact that it extends infinitely along the y-axis, but also infinitely upward. But more generally, the point here is that this is something in Calculus 3 we will refer to as being a cylinder. So in the next video, we will begin our discussion of sketching quadric surfaces. So stay tuned and take care.